So let's continue discussion of the QCA, and this time I'm going to focus more on the concrete one example, and then I'll try to develop some theory behind it. So here is a Hamiltonian. Well, you will object that it is Hamiltonian because you might think that Hamiltonian is always in the by H. But what I mean is that the Hamiltonian consists of the negative sum of all possible terms drawn on this side. So there's a three-dimensional cubic lattice with the 2 qubits per link, which are distinguished by 1 and 2, and there are 8 type of terms. This is one instance of so-called Walker Wang model. The Walker Wang model is not really a model. So maybe I should write down a proper. Okay. So the Walker Wang model is a special instance. So let me give you more context. The Walker Wang model accepts possibly modular or premodular tensor category, and then produces a lattice model written down on 3-dimensional lattice. So the modular tensor category is supposed to explain the anyon theory in the 2 + 1 dimensions. Here we are talking about 3-dimensional Hamiltonian, 3 + 1 dimensional theory. So what's the connection? The ground state of the 3-dimensional Hamiltonian is supposed to be the superposition of all possible word lines of the underlying anyon theory explained by this modular tensor category. And so the ground state is going to be, it has some vacuum components, and it also has some other loop configuration. It may have some link diagram inside, and this list just continues. By convention, we can fix the amplitude in front of vacuum to be just 1, and you can wonder what these amplitudes should be. And these are provided from the modular tensor category when you interpret these word lines as if the diagrammatic calculus. The diagonal calculus from the modular tensor category gives you a complex number, and that complex number is precisely this amplitude. So there is a very general prescription how you can write down a Hamiltonian given a modular tensor category, and you can even define a pretty broad class of a 3-dimensional manifold. Here, we don't worry about that generality. We only focus on one particular example, and this particular example has an input category, so-called the free fermion theory. The three fermion theory consists of 4 objects. It was mentioned in one of the lectures this week. There are 3 fermions, each of which, so other than the vacuum, each of which has a topological twist -1. Therefore, it is called fermion. And they braid non-trivially by -1. So that's all the data you have to remember. The F symbols are all trivial. And this construction does not really follow the Walker Wang's original prescription, but if you interpret the spirit that the ground state should be the superposition of amplitude configurations with amplitude corresponding to the correct quantum amplitude, then this gives a correct bulk Hamiltonian. Yeah.
Is there any way for me to remember your Hamiltonian? This is not mine. This is yours.
This is not even mine. It's recorded in a paper with Fiona, Lucas, Xie, and Ashwin, I believe. Yeah.
But is there any way to remember? So
no, yeah, there is a prescription. So let me, not too in detail, but briefly discuss that. So it is easier to think of this simple cubic lattice with the 2 qubits per link as a interpenetrating 2 simple cubic lattices. So there is a plaquette, then there is a penetrating link, and you assign a qubit for every link, including the dual one. And then you assign, you think of the one lattice edge to be occupied by, say, F1, and the other occupied by F2, if they are in the state 1, or unoccupied if 0. And then, well, because of this configuration, the word line of F1 and F2 are never intersecting. So there's no ambiguity to talk about whether they are linked or not. So if they're linked, then you assign -1. But how would you implement that linking in terms of Hamiltonian? Hamiltonian terms are designed to fluctuate the word lines. And whenever it crosses, whenever there was a line and then you insert a plaquette to map your word line to go around it, then you probe whether there is a F2 that is going through it. And if there is one, then you multiply your amplitude by -1. And that calculation is all local. And these Pauli matrices are capturing those calculations. The important property of this Walker Wang model is that you can introduce interesting boundary condition. So you always imagine a boundary attached to a three-dimensional bulk. In the bulk, you have original Hamiltonian. And at the boundary, you assign a different Hamiltonian whose terms are explicitly you can write down. In this case, it is just a truncation of the bulk terms at the boundary. So this theory is not supposed to have any bulk topological excitation. It follows from the modularity of your input tensor category, because, well, very, very pictorially, if you ever had an excitation, meaning some string that is terminating at some point at the bulk, then there could be, in your superposition, there is a configuration that looks like this. And there is and this configuration can be implemented by some plaquette operator acting there or acting there. But since the string is terminated and my input modulo tensor category is non-degenerate, in other words, the presence of word line can be detected by some other ennian. And if I pick the other ennian to be occupying this word line, the small one, then this amplitude becomes ambiguous because the string is terminating. The fluctuation operator that inserts this auxiliary ennian could be inserted this way or that way, and depending on how you do it, the amplitude will be different, and that's not allowed. Yeah.
Are these world lines of F1, F2, F3, or are they?
You get to choose only two.
Okay.
Yeah. So the fusion group is Z2 cross Z2, so you pick two generators of it.
Okay.
However, the word lines may end at the boundary, and that's the role of your boundary terms. It makes your amplitude pretty well defined, even if the word line is ending there, and you can work out the contents of the resulting ennian theory effectively at the boundary, and you realize that it is exactly the same as the input category. So that's a little bit of background on the Walker Wang model. Now, the question I want to ask, is the disentangling. So by other machinery developed by theoretical physicists, that there does not exist any interesting state other than the trivial state in 3 dimensions consisting of spins. So here, interesting or uninteresting means that you can, whether you can map the state, given state, to a product state. And here, the transformation is supposed to be a constant depth quantum circuit. So people have believed that the ground state of any three-dimensional Hamiltonian that is gapped, if there is a unique Hamiltonian, then there must exist a unitary that maps this ground state down to the product state. Now, we got to test the belief, and we tried and failed. So we get to think about why do we fail. So let's get to that.
Sorry,
yeah.
Suppose you took like a digraph wind peak, wind peak, so that has a topological ground state. That's not related to all of, is it?
Digraph rhythm theory, well, you can, if you write down the SPP side of the digraph rhythm theory to have a unique ground state, then almost by construction, gives you a circuit to disentangle it. The interesting piece on the digraph rhythm theory is that you have a symmetry. If you,
finite group?
yes.
I see. So what is the basis of this hypothesis?
I'm not the best person to ask why that has to be the case. Yeah, I don't have a good answer, but people say that. Okay, so, but when it comes to disentangling, I want to distinguish two problems. I want to propose two problems. So the very problem is this. But we don't really work with the we don't really work with the ground state per se. We only see the Hamiltonian. So probably our calculation is based on the Hamiltonian. So we may think about equivalent sounding a problem to map a given Hamiltonian to a trivial Hamiltonian, which I will write as like that. So on the H naught, everything is just a single qubit sigma z. The ground state is trivially all zero state. Nothing really interesting happening. I could modify this Hamiltonian to include other terms, but still preserving my triviality of the ground state, just like this, where J and J prime are nearby. I didn't do anything about on the ground state, and you can keep playing the same. You can multiply various terms together to make another Hamiltonian with the same ground state. So I want to treat all of these, the sum of possible local products of sigma z's, as a trivial Hamiltonian. Now my question is, the problem is, whether there exists a unitary that conjugates this given Hamiltonian to this trivial Hamiltonian. Yeah. Now I want to conclude, well, I will conclude in the end that the Walker Wang model, the very Hamiltonian, is not going to be disentangleable in the sense of second, in the sense of disentangling Hamiltonian. So let's discuss why that has to be the case. Yeah. Suppose, to make a contradiction later, suppose there is such one. The beauty of quantum circuit is that you have many gates that implements your desired V. So the entire thing is V. But you get to erase it. There's no problem with that. The some gates can be dropped and it's still a quantum circuit of constant depth. No problem. More generally, in view of our discussion towards QCA, this means that there is some action implemented by V, conjugation by V here, and you can introduce a spatial boundary with some fuzzy action in the middle, and here you get action of identity. And there exists a modified, say crossover, there is a modified unitary that implements the given action in some region of the space and identity action on the other half of the space. So, or blend. Okay, so this is the property I need. I'm going to argue that the Walker Wang Hamiltonian for the three fermion theory is not Hamiltonian disentangleable by any unitary that blends into identity. Okay, so now I'm going to consider the boundary, because the boundary is the only interesting piece in this discussion of the Walker Wang model. And I'm going to introduce, say, three pieces, A, B, and C. The size of A, B, C are somewhat arbitrary, but sufficiently larger than each term's range. Maybe 10 times larger, but that should be enough. So what I'm going to do is I'm going to make a blend of my disentangling unitary only on this region. So in the quantum circuit picture, I want to keep all the gates here and drop everything there. The height is chosen such that the blending region is contained in B. So the action of my hypothetical disentangling circuit is what I wanted, what I assumed in C. In A, it does nothing. Okay. So the original Hamiltonian is now passing through this my disentangling circuit. Oh yeah, well, let's do this. So I'm going to compare the original Hamiltonian and the other. This is original, and this is the conjugated version. What are terms here? Well, let's remember what we mean by trivial Hamiltonian. Oh, yeah, those matrices are discussed later. The trivial part, so in this region, the terms will look like just sigma z. Probably there is some product of those, but these products do not interfere with the single qubit ones. So the disentangled Hamiltonian on the ground state, it ensures every qubit is in the one particular state. I have no idea on the intermediate region because I have not defined how I interpret here. Here I keep everything. Nothing is changed. Okay, so since I have a sigma z enforcing ground state to be in the zero state in this region, if there is a term that overlaps this region, say I have, I don't know, sigma x to the 10 and exponential to like, well, say I minus 1 to C6. Well, suppose I had such a term. Then using the knowledge that on the ground state, the sigma z takes +1 eigenvalue, I'm free to remove any sigma z as long as that one is supported on region C with the scalar 1. That transformation does not affect anything about the ground state. Well, let's assume that we have done that. Then any operator element that would have touched qubit in this region is now replaced by scalar. So the resulting Hamiltonian after this rearrangement is now supported on this A and B only. How thick was the region? It was like maybe 20 times the interaction range, a constant. How large was that side? Well, as large as you want. So what is this? This is 2D Hamiltonian. So by assuming disentangling transformation on the Hamiltonian level and using the fact that it blends into identity, we were able to restrict the three-dimensional Hamiltonian down to two-dimensional Hamiltonian. But we didn't do anything about the boundary, the spatial boundary. So whatever topological particle content you had in the original Walker Wang model is still there. And we didn't have anything in the bulk. So when it comes to the topological particle content or any abstract description of it, that doesn't change. So we have successfully, under the assumption of hypothetical disentangling circuit, we have obtained two-dimensional Hamiltonian realizing the three fermion theory. What's wrong with the three fermion theory? Well, nothing wrong, but except I want to note this formula. There's something called chiral central charge associated with the modular data, which you can compute. And for the three fermion theory, it is just -1. In particular, C minus is non-zero. And let me invoke another belief in the community that the two-dimensional Hamiltonian that is commuting will not realize anything that is chiral. But there's a condition. It has to be commuting. But is our Hamiltonian this commuting? We started with a commuting Hamiltonian. I didn't explicitly check, but you can enumerate all possible combinations of commutation relation and check that they are commuting. The disentangling circuit is an automorphism. It's an operator algebra automorphism. So it preserves all the commutation relation. In particular, commuting terms are mapped to commuting terms. So, and at the rearrangement step, all I did was just replacing an operator with its eigenvalue. So commutativity is just preserved, and our HAB is a commuting Hamiltonian, realizing the three fermion theory that is chiral. So it goes against the belief. Yeah.
Could you review in your picture there? You're doing two truncations. One is left to right, and the other is vertical. Can you?
Oh no, there's no.
It looks like.
Oh yeah. Okay. So the red thing was actually a boundary in time, quote unquote. So before transformation and after transformation, I want to.
Okay, so it's only one gradient.
Yeah.
Okay.
Okay, so how strong is the argument depends on this Hamiltonian Pauli matrices?
Not much. So all I needed was that. Well, yeah. All I needed was explicit this form. So I wanted a single qubit operator in the hypothetically disentangled region to be just a single qubit Pauli. You may say that's a strong, but other than that, I do not assume anything about Pauli.
And the commuting property is preserved in this truncation?
Yes.
the question
Is there some particular reason that you've chosen 3 fermion as opposed to some other theory with with a chiral central charge like semyon or something?
No.
Okay.
It looked easiest. I'll come to that in the very last part. Okay. Now let's employ some of the techniques that I explained on Monday. So, yeah, we just argued that there shouldn't be any disentangling circuit that disentangles a Hamiltonian. But we shouldn't give up, and exploiting the fact that it consists of Pauli matrices, we can make some progress, and that will give you our QCA. So let me just remind you what we discussed on Monday. I introduced a special matrix called, which I denote the epsilon, consisting of entries drawn from this Laurent polynomial ring. And the role of the interpretation of this particular matrix was that if you insert any column vector of Laurent polynomials that represents some Pauli operator, then the result of after this map is supposed to be the location of the excitations. If your Hamiltonian was a Pauli Hamiltonian. And then we discussed the co-kernel of this map and interpreted this co-kernel as the equivalence classes of excitations. Anything that lives on the codomain of this epsilon map is going to be some hypothetical excitation. Anything that lives in the image of this epsilon will be precisely those that are created by local operators. So if you mod out those by locals, then what you're left with is the notion of topological charge. Well, there was a discussion about the torsion submodules and others, but that's technicality, but this is the morally that one. Here, we started with the Walker Wang model based on the modular tensor category, which does not have any topological charge in the bulk. So the co-kernel must, quote unquote, vanish. Technically, only the torsion part should vanish, but yeah, let's not worry about that part. But what does that mean for a co-kernel to vanish? Every excitation, every hypothetical excitation that is represented by some element in the codomain is now going to be included in the image. But what does that mean in terms of this matrix? It means that for any unit vector, and this is my matrix, there exists a column vector that gives this unit. That's what it means to have the 1 in the image. But now let's interpret the epsilon once again. Epsilon was supposed to capture the location of excitations through the commutation relation to the Pauli operator. So it means that if I interpret this column vector, the one that is guaranteed to exist to provide this 1 unit vector on the codomain, then this commutation relation with the Hamiltonian terms is flipping exactly 1 term, nothing else. So that leads us to, well, maybe this is time to talk about a notion of separator. So locally flippable is an adjective, so let's talk about the separator first. Separator is a set of operators, not necessarily Hermitian, set of operators. I label it with A, such that if I assign eigenvalues to this operator, so when it's a qubit system, then the eigenvalue possible is just plus minus 1. So I think of a subspace where the eigenvalue of this is some given number. So the assignment of eigenvalues f determines some subspace, the common subspace of this. Oh yeah, I forgot. It's commuting. Then I demand, by saying that it is a separator, that it has dimension 1. So the name is chosen to reflect this. These operators, the eigenspectrum of this, so the spectral decomposition of these commuting operators are giving me a basis for your Hilbert space. You're slicing your Hilbert space off by the eigenvalues of these operators. Well, the trivial example is just the sigma z acting on each qubit. The usual basis coming from that. But that could be something else. And the locally flippable means that there exists another set of operator that I will denote by x, such that it anti-commutes with exactly one ZA and nothing else. And they are local. So you can, so yeah, locally flippable. There is some local flipper that just tosses one exact element in your separator.
But they're not separate themselves. Actually, they are not separate. They just
well, you can. Well, so it doesn't have to be, but they can massage to be so. Yeah. Okay. So this discussion, using the absence of topological charge, interpreted in terms of co-kernels and so on, these operators, one that is found by the vanishing condition, they are the flippers. You are flipping exactly one a term in your bulk. The rows of the epsilon is supposed to describe the one element of a separator. What do I do with that? Okay, so suppose I have some maybe some n qubits, and I suppose I had a locally flippable separator, so I will denote it by pair. And I have the same system, but I have the usual, the Pauli Z and Pauli X pairs. If I map each Pauli Z into element of separator and Pauli X to the flipper, then this map is an automorphism. Why? Well, everything is mapped to something, and due to the commutation relation, this map has to be injective. And I didn't say, but you extend this mapping by linearity to all possible combinations of operators. So, but injective map from a simple algebra has to be automorphism. And the crucial requirement for QCA that it preserves locality is implemented in my definition of locally flippable separator. I may have omitted the condition on the support size, but yeah. So, yeah, the notion of locally flippable separator applied to this Walker Wang model, mixing with the observational on the excitation map, gives me a QCA. And that is automatically disentangling the Hamiltonian. Hamiltonian terms were corresponding to separator. And the only implicit part is how to find the flipper part. But that is guaranteed algorithmically. Yeah.
So the claim is, so ZA and XA are just arbitrary, locally separable, or locally flippable separators. And the claim is that you can always use Pauli operators, and that it's a QCA that maps between them.
So the claim is if you have a locally flippable separator, then you automatically have a QCA. The locally flippable separator part doesn't have to be a Pauli type. But it mimics Pauli because their commutation relation is similar to the Pauli. Yeah.
So it says we can simultaneously disentangle this ground state, excited state, all those.
Yeah.
It's obvious that it means every dimension every eigenspace is one-dimensional. The
Yes.
ground state is one-dimensional, so the rest is also one.
Right. Yeah. Technically, attentive listener might have pointed out that the co-kernel was quote-unquote vanish. What is true is only the torsion part is vanishing. But there's other machinery that can handle this. You can compress your representation of a Hamiltonian in such a way that everything is independent from each other, and you can make the co-kernel literally vanishing, and everything just goes through. So we have started with the Walker Wang model, just to recap, Walker Wang model with the particular chiral surface topological order, and then we have argued that there does not exist any disentangling transformation that can blend into identity, such that it disentangles the full spectrum of the Walker Wang model. That doesn't exist. Well, based on the belief that the commuting Hamiltonians cannot realize chiral theory. And so for quite a while, this is the only example. And let me develop some, a little bit of digression into the Clifford part, Clifford QCAs. So the goal of this part 2 is to make you understand what it means to talk about the Witt group of anti-Hermitian forms. Yeah, I will get to that. So this is based on the polynomial formalism handling the Pauli operators. Let me start with the reminder. So once you express your Pauli matrix in terms of Laurent polynomial, the prescription is that the exponent of your monomial remembers the position, and the coefficient of that monomial remembers whether you have an operator or not. There's an X and Z part, but yeah. And you can study this relation a little bit further to conclude that if you give me two Pauli operators, each of which is represented by a polynomial, and if I sandwich this particular matrix of those polynomials, then you will get some polynomial here, some x5 plus or minus 1, and something like that. And there is a preferred basis with respect to which you write your polynomial. Specifically, you encode your sigma x part on the upper part and sigma z part on the lower part. Then this product gives you some coefficient, and that encodes whether the given two operators are commuting or not. This is no hard thing, but it is rather tedious to keep track, well, go through the argument, so I'll skip that. Yeah, the constant term, if it is 1, then they are anti-commuting. If it is 0, then they are commuting. Now, looking at the commutation relation using this lens, what does it mean to have a QCA that preserves all the Pauli operators to Pauli? Traditionally in the quantum information and computing community, Clifford gates are those that maps any Pauli operator to a tensor product of Pauli operators. So I quote that adjective Clifford to decorate QCA. Clifford QCA is one that QCA, but it maps a Pauli matrix to another Pauli matrix, or possibly products thereof. This is an automorphism. So in particular, it must preserve the commutation relation. But commutation relation is now encoded by this bilinear form. So your QCA, if I write each column to be the image of single qubit Pauli X, the next one to be the image of single qubit Pauli X, but some other location. And so if I enumerate all of them, then this matrix must satisfy this equation. Here the dagger, Here the dagger means you take a transpose of the matrix Q, and then you invert every monomial to its inverse. You take an inverse of every monomial. So Clifford QCA is basically captured by this single equation. There's no other information you need. Well, there's one information that you forgot. If your QCA is purely consists of single qubit Pauli matrices, you are conjugating an operator by a quantum circuit of depth 1, where gates are just Pauli operators, then the only effect of that is you are changing the sign of some Pauli operator. So, but sign you are promising to handle later, and we are focusing on the non-sign part, the operator part, and that operator part is captured by a single equation here, over Laurent polynomial ring, where the number of variables is equal to the spatial dimension. Now, in Matt's talk, we were told that it is important and interesting to think about the boundary. Just to recap, what was the boundary algebra? You consider the operator algebra on some half of your space, map this full algebra by your QCA, and then there's something that is leaking out, and anything here is still there because the QCA is invertible. So that one that is smeared out, you call it boundary algebra. How can I capture that in this algebraic formulation? I want to think about the system as a stack of one-dimensional lower systems. So each of them is the lattice of dimension one dimension lower, and the full thing is lattice of dimension d. And if I group sufficiently large block size then your QCA will be acting on the image of your single qubit operator will be supported on just nearby 3 layers, right? Well, here I'm relying on the strict locality. It's just grouping several slices together, and you declare as a new slice. And we learned that there is a shift QCA that shifts everything to the right or left. So since we know it, we are comfortable using it. So let me just push this part here. So the QCA is now acting on, well, the image of QCA for a single qubit operator is now supported on just 2 nearby layers. That's fine. But how does that manifest in terms of this matrix? The matrix entry of Q consists of the image of your Pauli operator, and the coordinate, the exponent of your variable will record the position. So to say that this operator is supported on just 2 layers, it is equivalent to say that, oh, this column vector decomposes into 2 pieces where each of them does not involve variable z, and there is a 1 z factor of exponent 1. Right, so QCA, well, image of single qubit on 2 layers. In the Clifford side, that means Q is written as where A and B don't have C. Yeah.
So when we try to group different layers, do we increase the dimension of Q?
Yes. Oh, yes, yeah, precisely. Okay, so we have reduced one variable, well, nominally, and you can prove things about these 2 matrices, A and B. And here are the results. So the matrix rank of A is always an even number. So does the B. And more interestingly, the kernel of A transpose dagger times that symplectic matrix is equal to the image of B, and symmetrically for B. So now I want to consider this particular matrix. So I started with a Q, decomposed in 2 pieces by factoring out the z factor and writing as a linear polynomial in z, and then I read off the constant part. You can do the b part, but that's symmetric. You can constant part, and you can show that this is congruent to something here and everything 0. Okay, so that sounds like a pretty distant manipulation of matrices. Why do I do that? Because it is interesting. This matrix has a number of properties. First, it is anti-Hermitian. You may wonder, what does it mean to be anti-Hermitian over binary field? But you can generalize to any, at least prime dimensions, so anti-Hermitian makes sense there. And the C does not have diagonal constant terms. This piece is trivial when you work with the field, the qubits with prime dimensions, odd prime dimensions, but non-trivial for qubits. So I include it. And you can also show that determinant is some square number. And here is an example. So the three Fermion Walker Wang model, you can compute the QCA according to the quote-unquote algorithm I sketched. And you can figure out, you can block the layers side by side and expand in the third coordinate in linear fashion and extract the constant part, make a anti-Hermitian matrix, then and you manipulate it using some congruent transformation to make it look nicer, then you end up with this simple form.
So, Jeongwan,
Yeah.
I think this QCA is order 2. So it's easy to see from here, it's order 2.
No.
So that's a different.
I'll get to that. Yeah. Actually, it's quite, well, for me, it was very rewarding to see this calculation. You think about the situation more formally, and you know that there's an algorithm. You go ahead and let the computer do it. You end up with the gigantic matrices. So I feel like I conquered the gigantic matrix by thinking. Right. Okay, so why is this interesting further? Yeah, so the theorem is that for a given anti-Hermitian form like this, satisfying these conditions, that it has to be anti-Hermitian, does not have any constant diagonal term, and the determinant is non-zero, then there is a Clifford QCA from which you can induce this form again. The beauty of this is that this QCA lives on d dimensions. This object involves d minus 1 variables. And another thing, if your anti-Hermitian matrix is congruent, stably congruent, so you add in some symplectic auxiliary thing, if this is congruent to another symplectic matrix of a slightly larger dimension, then QCA is actually a Clifford circuit.
Are they all order 2?
Sorry?
Are they all order 2? This new one?
No. Yeah, well, there's no order here. Yeah. Another fact, well, if you combine two Clifford QCAs, alpha and beta, then there will be corresponding anti-Hermitian matrices. And the anti-Hermitian form of the composition is actually the direct sum of the two. Therefore, you are fully justified to talk about the Witt group of the anti-Hermitian forms. So, what is a Witt group? We have heard about the Witt group yesterday, the Witt group of modular tensor category. This is more classical. Just for your context, the Witt group typically over a field, say F, is a collection of non-degenerate symmetric forms. You think about all possible those, and then you mod out by the equivalence relation that if a symmetric form direct sum minus of another symmetric form ends up being congruent to the hyperbolic space for some number of them, then you tell them they are equal. Here, the only change is that now this is anti-Hermitian. the field is no more a field, but a ring of Laurent polynomials. And this whole, well, yeah, the only change is that. So we have reduced, well, although omitting all the detail, we have reduced the study of the Clifford QCA down to the Witt group of anti-Hermitian forms over one less number of variables. Yeah, and now you can talk about the exponents. It's a simple theorem, but let me just state it without proof. If your field had exponent, say n, as in the traditional classical Witt group, then this has the same exponent. So if you had a Q trit, for example, then it corresponds to you are calculating the Witt group with respect to coefficients in the F3, and there the exponent is 4. And if you have a Q, 5-dimensional qubits, then you have this, and exponent is 2. Qubit is an exceptional thing because the Witt group over the binary field is, well, you need some care, but over the anti-Hermitian setting, there's no subtlety, and exponent turns out to be 2 again.
What's the exponent?
Sorry?
What's the exponent otherwise? Or what's the exponent otherwise for F2?
Oh, I actually don't know the proper, honestly, I didn't study the Witt group over binary field. Well, characteristic 2. Yeah. Okay, so for the remaining time, well, so let's do some fun exercise in the world of the anti-Hermitian forms. So in the morning, Matt stated that the 2-dimensional QCA in the general setting with a strict locality turns out to be the trivial one. Here, trivial means that circuit or shifts. And the argument was to look at the boundary algebra and decompose the boundary algebra using the visible simplicity down to a trivial one, and therefore we get the correspondence. Here, very similar thing, but nominally they look very different, can be done. So we look at the anti-Hermitian form over now one variable. So we look at the anti-Hermitian form over just one variable, and I claim that they're all trivial. And this is simple enough that I can do here. So let me do that. The one variable polynomial ring is so special in that the Euclidean algorithm works. You give me 2 polynomials, and I can find their greatest common divisor by a efficient algorithm. And that means that that saves a lot of effort. That means that if I look at this anti-Hermitian form, which is originally over this polynomial ring, but now I want to think of it as not over the polynomial ring, but just over the field of functions. So this is this consists of f of n gx, where gx is non-zero. Why is that? So if I have, suppose I have trivialized this using some transformation. And now here E can take elements inside this from the function field. Then you can, you can rearrange the denominators of these matrix elements here. You can push all the denominators to the one side, and you're left with the numerators. And you think about the determinant of this E, and realize that their greatest common divisor must be 1, otherwise it won't be invertible. Then you can decompose this matrix into in such a way that it uses only elements from the integral elements. So in this one-dimensional ring, showing the triviality over the functional field is the same as showing the triviality over the polynomial ring. And how do you show the triviality here? I'm going to use induction. All I have to do is to find some congruent transformation that gives me 0 on the upper left corner, because that means then I can further reduce the dimension and use the induction in dimension. If C did not allow any transformation that ends up in a 0 in the upper left diagonal, what does that mean? That means there is some transformation, E, such that now my form is completely diagonal. Everything else is 0. And if I look at this equation, then it would look like this. But these elements, now we are working over the characteristic 2, these elements live in the field of x squared. These elements live in the field of x. But this field as a vector space over that is dimension 2. So if your summation has more than three or more terms, then there is a linear combination of dAs such that the result is 0, while VAs are not 0. So we are finding 0 on the upper left corner, and using induction, it becomes trivialized. So two-dimensional QCA Clifford type is going to be trivial. Okay, so what about then the further? Let's move on to the more examples of three-dimensional Clifford QCA. We're now leaving the algebra part, but more the pictorial part. So there's another construction of Walker Wang state based on the coupled layer construction. You throw in many states and stack them on top of each other. But with the rule that on the upper sheet, you plug in Sumanian theory. And on the lower layer, you put the conjugate. So the total of 2 sheets are now realized by some Hamiltonian system, no problem. And then we use the Swindle argument. We are going to kill 2 states pairwise, but now on a different pair. So you find a boson in this double layer system, where one copy is C and the other copy is its reverse. You find boson, and then you drive strong coupling that fluctuates this boson. Then in the bulk, you will be left with no topological excitation because you are going to condense all of them, and some anion should break non-trivially with the condensed boson, so it should just disappear. And in the end, what you're left with is some bulk state that looks trivial without any topological content, but at the boundary, you're left with the input category. You can do a concrete calculation based on this idea, and the calculation is not that trivial. Even if you find the boson in this bilayer system, their operator that fluctuates them may not communicate with each other. Then you have to decorate them properly, and it can be a mess. But fortunately, for the simple theories of fusion root whose fusion group is ZP, this can be done, and the ending result is that the Hamiltonian will be some Pauli operator again. But this time not necessarily qubits, but some higher dimensional ones.
So Jeongwan,
Yeah.
when you say boson, do you mean Witt and anion, or we can now?
Strictly boson.
It will be a Witt.
Yeah. So yeah, So using this construction, you end up with the group of QCAs. Oops. That looks like this. So as far as I know, modulo upcoming results from you guys, this is the only examples of non-trivial QCAs. Well, hypothetically. Well, hypothetically non-trivial only because the non-triviality of this QCA is based on the assumption that commuting Hamiltonians, whatever two-dimensional topological order you realize using commuting Hamiltonians, there gotta be a boson in the bulk. That's a conjecture. In modular conjecture, these are all non-trivial, and there are infinitely many.
Sorry, this is a proposed classification of Clifford QCAs, or what?
Yes, yes.
Is your category C modular or not? It's a modular one.
Oh, here?
Yeah.
I would like it to be modular.
Okay.
Yeah. Okay, so to what extent this is rigorous? This is non-trivial against Clifford circuits. That much is proven. This is likely non-trivial, well, although some people may not agree, against general circuit. Yeah, and this assumes various conjectures regarding commuting Hamiltonians. Let me mention that conjecture more in a perhaps more memorable way. I think this is true. I don't have proof. For any commuting Hamiltonian, if you open up in 2 dimensions, if you open up a spatial boundary, there is a maximal set of local operators such that is this is a formulation of what it means to gapping out. So people say we gap out this boundary and so on, but what does that mean? I interpret in the following. So give me a commuting Hamiltonian defined on a 2-dimensional lattice. I open up the spatial boundary, and I only keep the terms strictly inside one side. Okay, so there will be some qubits. They may not be touched by any of these terms, but some of them will be touched. Now, I want to consider the commutant of the terms of this Hamiltonian restricted to this on this boundary. And I want to find a commuting subset in that commutant in such a way that there's no further place to put in other terms. You are exhausted. And the measure of exhausting or not will be, I think, given by the local TQ condition. Local TQ condition is one that if you give me a local patch and if you collect all the terms that intersects this region, then the ground state of this restricted Hamiltonian matches the resistance matrix on that patch, matches that of the global ground state. So your local terms are sufficiently strong to tell you that, oh, in this patch, the ground state must look like that. It just determines. That's what the local TQ condition means. And I conjecture that for any 2-dimensional local Hamiltonian that is also locally, local TQ condition is met, then whatever boundary you open, you will be able to gap it out. If this is true, then there is a better hope that we can prove for any such commuting local Hamiltonian in 2 dimensions, the corresponding annual theory must have a boson in it, non-trivial boson in it. And if that conjecture is true, all the 2 steps are true, then these non-trivial examples will still non-trivial. Even the direct sum part will be non-trivial. So, coming back to the QCA, the situation is well somewhat primitive yet, in the sense the only example that are constructed all come from Clifford type. I am hearing some exciting developments recently, but we will see later, I guess. Yeah. Before I'm mentioning open problems, let me mention one thing. So Matt this morning characterized the boundary algebra using the notion of visibly simple algebra. The visible simpleness was that you give me an element in the visible simple algebra, and you pick a qubit inside the support of that algebra, then you are guaranteed to observe the simplicity of the algebra by finding another one that anti-commutes at that location. Here's another characterization of the boundary algebra. So I suspect it may have been discussed in some opera algebra context, but I have not heard any. So I imagine a subalgebra contained in the opera algebra on your lattice. Your lattice consists of spins, and the operator algebra is constructed in the usual way. You take a tensor product of finite remaining terms and take a limit. And I consider the subalgebra inside it. And I call it invertible if the following is true. A comes with a commutant. Let me denote it by B. And for any element in the mother algebra, there is a decomposition. Such that A belongs to A, B belongs to B, the commutant of A, and with the locality condition. The diameter of the union of support of all things should be smaller than some constant. And the same is true for B part. So it is just a standalone definition for a subalgebra inside the full algebra of operators. And here are some facts about it. It is always simple. I did not assume it. It follows from the definition. And trivially, it is invertible if and only if its commutant is. There is a local generating set. And A is invertible if and only if A is boundary algebra of some QCA in one higher dimension. So, and using this notion, it is pretty obvious that you can talk about the Witt group of the invertible subalgebras. The trivial elements are the algebras of this form. Yeah. So you may wonder, oh, what's the invertible algebras? It's all connected to the. Well, let's get back to this. So the invertible algebra that corresponds to the disentangling QCA of this Walker Wang model is precisely the hopping operators of fermions at the boundary. There is some fermion leaving the anion, living on the surface, and they are meant to be mobile. They are not fractants. So there must be some operator that annihilates anion here and creates there. And if you collect all those hopping operators, then that's precisely the boundary algebra. And it's invertible. And the anti-Hermitian form that I talked about, that is encoded in this polynomial, is nothing but the commutation relation among those hopping operators. Right. So let me conclude with open problems. Oh, my scribble is getting bigger and bigger. So we have introduced boundary algebras and other related concepts, different characterization of boundary algebra. So we at least have seen two, the visible simplicity and invertibility. They are equivalent. But they are too large. I mean, we're supposed to analyze the QCA by looking at the boundary, and that was successful when you want to show triviality. You just look at the boundary algebra and fully understand it and just write down what it is. And therefore, we conclude that the bulk QCA was trivial. But the object is too large, in my opinion. Too large in the sense that it's not a number or two. So, and I introduced the anti-Hermitian form in the special case of Clifford QCA, but even that matrix is not fixed. There is an ambiguity how you interpret the translation unit cell. And according to that interpretation, your very matrix form changes. So you must ask, and we have to answer, that under those reinterpretation of translation group, whether the Witt class that it represents changes or not. So we are, I think, is pretty far from having a fixed invariant for the QCA that detects, like an analog of the GNBW index for 1D QCA for shifts. We don't have that. The next question is the relation between the group of QCA, of course, modulo circuits and shifts, and, in 3D. And the Witt group of modular tensor category. We have identified a subgroup of the Witt group of modular tensor category coming from the Clifford QCAs. And they are genuine subgroups. There's nothing wrong with it. But it's far from having a proper relation. We don't have a map from one object to the other. Given a QCA, we can construct, we can consider the boundary theory by opening up the spatial boundary. Oh, I'm sorry. Yeah, given a QCA, you map the trivial Hamiltonian, the sum of all single qubit z's, by QCA. That gives us some Hamiltonian. And then you cut the space open and introduce boundary terms at the Hamiltonian, at the two-dimensional boundary, and study the Annian theory on that, and you can map it into the modular tensor category equivalence relation. But there is but this chain of implication is not firm. We don't know how to introduce the boundary theory in some canonical way. Well, it involves the slightly more difficult problem to my conjecture. My conjecture on the two-dimensional commuting Hamiltonian. There, you are considering the one-dimensional boundary. Now, here we got the three-dimensional bulk with a two-dimensional boundary. The reverse direction, given some representative of Witt class of the modular tensor category, can we construct a QCA that can reproduce it? Well, we only have succeeded in the Clifford case. I don't know any other example yet. I hope to see, but not yet. Yeah. And of course, the big missing piece is that why not higher dimensions? If you believe in the QCA and the Walker Wang construction, then, well, it is suggesting that you might want to consider the square root of any fractal phases. Whatever square root means. Yeah, it's still a completely open problem whether there exists anything in dimension 4 or higher. And the last question is, we have opened up the boundary of a QCA and studied the boundary algebra, and we have equivalent formulation of characterizations of the boundary algebra. But there's one unsatisfactory aspect. We had to fix the direction. The 3D, the QCA exists in there, and you can cut your system here or there, whatever. And we have no clue. Well, yeah, we have no clue whether how the boundary algebras across different directions are related. Maybe isotropic, but when and how? This question is actually intricately related to this one. So yesterday we learned that the Witt group of modular tensor category has a free part, meaning there is some category whose manifold delineate product does not end up in a quantum double. If we had a QCA that disentangles the Walker Wang model for that infinite order modular theory, then that QCA is presumably have an infinite order. But then we can juxtapose that QCA on the one dimension higher, like this. Now, the boundary theory depends on the direction. Boundary algebra depends on the direction. Along this direction, if I cut it up on here, then by definition, it interpolates to the identity. If I open it up to this direction, then you will have a non-trivial boundary theory for every sheet here, but every sheet here has an infinite order, so their sum will not be trivial. This problem goes away if everything were of finite order, because you can group them together to trivialize it, but we do not know. So, yeah, I believe there are many opportunities. Thanks.